Hey everyone, just wanted to make a quick video, put it out there for you if you need a little more help on the rational zero theorem. So this example I'm going to cover, this is actually problem number 20 from the 6.9 worksheet that you were all assigned yesterday. So I'm going to just work through this one, okay? The equation that is on the screen here, it's pretty sophisticated. You can see it's got 6 terms to it. And we don't really have many factoring techniques for something that's this large. So that's a good indication that I end up trying to use the rational zero theorem here. Now recall, the theorem wants you to focus on 2 numbers in your equation. So it wants you to focus on the constant. So this 8 is your constant. It's going to lead you to the p-values for the theorem. Okay, so p is going to be any factor of this constant 8. So that would be plus or minus 1, plus or minus 2, plus or minus 4, or plus or minus 8. And then the theorem also wants you to focus on the leading coefficient, which in this case is just a 1. That 1 will lead you to your q values. Now, the only factors of 1 are plus or minus 1. And then the theorem tells us, take the list of p's, put it over the list of q's to make all of your possible rational zeros for the equation. So the nice thing about this is, since q is only plus or minus 1, then basically your list of p's, when you put it over your list of q's, doesn't change. That means p over q is just going to be plus or minus 1, 2, 4, and 8. So if this equation has a rational zero, it's going to come from this list, okay? Now, there's a couple ways we can check which of these numbers from the list might work. I think the best way to do it is with synthetic division, synthetic substitution, okay? So I'm going to make a chart here to represent the synthetic substitution. And I'm going to put the coefficients from the equation up at the top here. So that would be 1, negative 2, negative 3, 6, negative 4, and 8. And then the value that I will be testing from my list of the p over q's, that's going to go over in the left-hand column. So the first number I'm going to test is a 1. So we begin the synthetic substitution. I bring the first 1, the first coefficient, down. I multiply that by the number that's in the left column. So 1 times 1 is 1. And then I add that to negative 2. The result gives me negative 1. Then the process starts over. I take the negative 1, I multiply it by the 1 that's in the left column. Negative 1 plus negative 3 adds to negative 4. Negative 4 times 1 is negative 4. Add that to 6. You get 2. 2 times 1 is 2. Add that to negative 4. You get negative 2. And then negative 2 times 1, if you add that to 8, you get 6. Now remember, in this process, that last number is always the remainder. We're looking for the remainder. We want it to be 0, okay? If it's a 0, then we can say the number that we were testing, in this case the 1, is a solution to the equation. We don't have that in this case, so we're going to rule 1 out. And we're going to move to the next number in my list of p over q's. So the next number I would test would probably be negative 1. Bring the first coefficient of 1 down. 1 times negative 1 is negative 1. Add it to negative 2, you get negative 3. Negative 3 times negative 1 is 3. Add that to negative 3, you end up with 0. 0 times negative 1, if you add that with 6, you get 6. 6 times negative 1, if you add that with negative 4, you get negative 10. And then negative 10 times negative 1, if you add that with 8, you get 18. Clearly not what we're looking for. We want a 0. to finish, so I'm ruling -1 out also. So both plus and -1 from my list are ruled out. Now I move to, I'll try +2 next. Bring that 1 down. 1 times 2 is 2. Add it with -2, you get 0. 0 times 2 is 0. Add it with -3. -3 times 2. Add that with 6, you get another 0. And then 0 times 2, add that with -4, you get -4. -4 times 2, if you add that with 8, bingo, you get a 0. All right, so there's our first 0 or solution to this equation. And now I can take the equation and I can factor it slightly. I can say if 2 is a solution or a 0, then that means x minus 2 would be a factor of the equation. And then I'm going to use these numbers to come up with another factor. It would the 1 would represent the coefficient on x to the 4th power. And then I'm not going to put a 0 in. I'm going to skip a term and I'm going to go minus 3x squared minus 4. Okay? And now the focus is on this trinomial here. We're trying to figure out the zeros or the solutions to that. Okay? There are two approaches you can take here. Okay? You could try factoring. At this point, the hope would be you'd recognize that that is factorable. Okay? It is in quadratic form, so it is going to factor to two binomials that both begin with x squared. And one is going to have to be a -4, the other is going to have to be a +1. And then, of course, you want to carry down your x minus 2 here. Okay. From there, we could set x squared minus 4 equal to 0, and we could set x squared plus 1 equal to 0. And those are both pretty easy to solve. I can just add 4, square root both sides, x equals plus or minus 2. And similar over here, I can subtract 1, square root both sides, x equals plus or minus I. And then don't forget about the first value of x that you had from your substitution up there. So in total, you will end up with 5 solutions. Okay. Now, let's suppose you didn't recognize that this trinomial right here was factorable. Okay. So your other option at this point, you could try P's and Q's on that trinomial. Okay. And you can use the same list of P over Q's from above. You don't have to test +1 and -1 again, because if they didn't work on the larger function, they're not going to work on this factor of it either. Okay, so your other option, we could build a new chart here, and I'd want to account for placeholders again. So I would put a 1, 0, then -3, then 0, and -4. And I would begin by testing the value of 2. If 2 worked in the first table in that process, then there's a chance it could work again. Okay, so we'll begin the process. We'll bring the 1 down. 1 times 2 is, of course, 2. Add that with 0, you get a 2. 2 times 2 is 4. Add that with -3, you'll get a 1. 1 times 2 is 2. Add that with 0, you get a 2. 2 times 2 is 4. Add that with -4, you get a 0. So right there, that just shows you 2 works a second time. And at this point, we would take it to a factorization. We have the initial x minus 2 and then another x minus 2 off of this new 0. followed by these four values will lead you to a factor of x cubed plus 2x squared plus x plus 2. All right, now at this point, you got, again, a couple options. Now we're focusing on this cubic factor right here. You want to try and find the solutions or the zeros of that. My hope would be you'd recognize that's factorable by grouping. Okay, so notice if we group these two terms together and these two terms together, we'll be able to pull out an x squared. That would leave us with x plus 2. And from the second pair of x plus 2, you can pull out a positive 1. And then notice those are identical. So I'm going to carry down the first two x minus 2's. Then these come together to give me x squared plus 1. And the x plus 2 is written one time, we know, in the grouping process. Okay. So then we're focusing on both of these. I can take the x squared plus 1, set it equal to 0. I can take the x plus 2, set it equal to 0. It's going to lead me to the plus or minus I and the negative 2. In addition to the 2 that we got twice from the first two divisions. Okay. Now, maybe you didn't see that the cubic up there grouped. If you didn't see that, then you could try P's and Q's a third time, and that should have led you to negative 2 working. And then from there, you can get to the plus or minus I. All right, so hopefully that helps you guys with the rational zero theorem a little bit more. Remember, this is your last technique for solving an equation for finding its zeros. You always want to try other factoring techniques first, if at all possible. Okay, so always be on the lookout for grouping to work or for quadratic form or sum and differences of cubes. All right.